Taylor Dupuy, and he will speak about arithmetic deformation classes in the sense of Buium. Please.
All right, so I'd like to thank the organizers for inviting me to speak here. It's nice to see everybody. Okay, so I'm just going to start.
Are there more lights?
No.
Can't see.
You can't see?
Nope.
I don't know, maybe I can do this. I mean, I don't think there is more. They were telling me that there isn't any more.
Is there a whiteboard behind it?
There we go. Yeah.
No, that's bad. That's very bad. That's very bad for this.
All right, it's like a spotlight, right?
Very good.
Is that better?
Yes.
Okay. All right, this will be weird. Okay, so this is kind of so there's this paper of Falting's, which is called "Does There Exist an Arithmetic Canard-Spencer Class?" And that's the title of the paper, and then the abstract is essentially no, right? And so what I want to show in this paper, or talk about in this paper, is how you can slightly modify his definitions that he's using in order to construct something that does behave like an arithmetic Canard-Spencer class. And okay, with that being said, I'm just going to start with the first section, which is abstract Canard-Spencer theories. Okay, and so I'm going to make a definition. So I'm going to define this category of schemes over S with a vector bundle with a vector bundle. Okay, so the objects are going to be pairs X and E, where X is a scheme over S, and E is a vector bundle on X. Okay, and the morphisms. So a morphism here from, let's say, X, E to Y, F, okay, is going to be a pair consisting of two things. F is going to be a map from X to Y of S schemes. And alpha is going to be a map from E to the pullback of F. So of vector bundles on X. Okay? So the example to have in mind here is the tangent bundle. Okay? And so I'm going to make another definition. So a functorially defined vector bundle is a functor E, so from schemes over S. So I'm going to use this E a little bit. So E is, I'm going to denote it as the functor, and it's going to be the image of the functor, which is the actual vector bundle, to this category of schemes with vector bundles. Okay, again, the tangent bundle is a good idea, but I'm also going to say such that the composition such that the composition with the projection here, so gives a closed subscheme. Okay? So, okay, and so an example is the tangent bundle, like I said. And so let me give a definition of what an abstract Canaro-Spencer theory is. So an abstract okay. So an abstract Canaro-Spencer theory will consist of I guess, a pair, E and K, kappa, okay, where E is from schemes over S to this functorially defined vector bundle. Functorially defined. Okay, and by kappa, I mean we're going to take kappa of Z, and this is going to live in H1. Oh, I forgot to give some notation. Okay, so I'll give the notation in a second. Of Z bar, E Z bar, for all Z in schemes of S. Okay? Such that, and I'll tell you what the Z bar is. Such that the following holds, dot, dot, dot. Where's my eraser go? So such that so those things you're going to think of as abstract Canaro-Spencer classes, and the condition that we want is that such that so for all f for x to y, we have the following d f bar of, so I need to explain what that notation is, star of kappa of y as elements in h1 x bar. Do I have a C bar? Okay, great. Okay, and so let me explain this notation real quick. So notation. Okay, so given, where am I? Okay, so if we're given f from x to y and e schemes over S to this functorially defined vector bundle, okay? VB, okay? What do we have? So, can't do that. Okay, so EF, okay, is going to be denoted by F bar DF, like this. So I told you that they were a pair. And this is going to go from x bar, ex bar, to y bar, ey bar. Okay? So this is going to be the closed subscheme of x that I was talking about. And these guys here are going to be the vector bundles on those x bars. Okay? And so in particular, we have these guys. Here. Y is going to be closed. Okay? So that's a CL for closed. Okay. So, great. Okay. So this condition is the important one here. So this is the important condition here. Okay, and essentially in the paper that I mentioned by Faltings, what he does is he assumes this property, right, and for a particular E, and then shows that for curves over number fields that they can't, such a compatibility can't exist. Okay, but I kind of tweaked it to make it a little more general, all right, and this is what we're going to use, yeah.
Sorry, just to keep something in mind, besides the tangent bundle, is there
Yeah,
something else?
the Frobenius tangent bundle is the other one. Yeah, yeah. So the Frobenius tangent bundle will be the sheaf of Frobenius derivations. Yeah, yeah.
But that has support, their X bar is still all of X.
So their X bar. So what you're going to do? So why I have to consider the bar is because what I'm going to do is I'm going to like take something and reduce it mod p, right? And the reduction mod p is going to introduce something as a closed subscheme, and that's what's going on. Okay, so that's what the bar is for. So let me give this example. So you were mentioning the tangent bundle. So here's an example. Okay, so the example is okay. So we can consider schemes over D1 of C. Okay, so this is D1 of C is C adjoint epsilon mod epsilon squared. So this is the dual numbers. Okay, and what I'm going to do is so here we'll take x bar. So given x in here, right? We take x bar to be equal to the reduction mod. So you essentially mod out by epsilon. So this is what's thought of as an infinitesimal thickening, right? E x bar here is the tangent bundle. So this is Tx bar over C, right? And kappa of x here. So this is going to be the Caviró-Spencer class of x. Okay. So this is for an infinitesimal thickening. Okay, and so this defines an abstract Caviró-Spencer theory. Okay, let me remind you of how this construction works a little bit. So let me just do a reminder of the construction. And I'm going to do it in families. So there's kind of three different variants that you can do for the Caviró-Spencer construction. There's one in families, there's one for a generic fiber, and there's an infinitesimal version. And they're all related. Okay? I'm going to describe the one in families really quick. In the infinitesimal version, you get by base changing. So for the KS, so recall, okay, that, so what we'll do is we start with a family, x over some base s. So I'll do it with a curly. So a big family here, x over s. Okay, so here's this picture, and here's our family. Usually it's going to be a flat family, F. Okay, and what we'll do is we take a vector here, okay, in the base space at some point S, and then we look at what happens in the fiber here. So this is XS. This is the fiber above this point. And so this picture is saying all over C. Okay? And what we do is we cover the fiber, right, by open sets, and we lift. So this is our derivation on the base. I'll do it with the curl of this one here. So we have this derivation here, and we lift the derivation to these open sets here. Okay? So we lift it in such a way so that it projects back down this horizontal piece exactly. But when we lift it on different open sets, we may get different vector fields here. Okay? So this is, say, delta I, and this is delta J. Okay? And what happens is when you subtract these two, you get something completely vertical since they agree on the horizontal pieces. Okay? So this is, we associate this di minus dj here, right? And we take the cohomology class associated to this difference, right? And you can see that, okay, again, this is the vertical piece of the tangent bundle. This is the horizontal piece of the tangent bundle, right? And the tangent bundle of the total space sits in an exact sequence, right? Where this is the kernel, and when you project down to here, okay? And so this guy here will live in H1 of XS, and it'll have coefficients in T XS over C. Okay, because we did it, so you can see that the difference of these guys is going to be completely vertical. That's what this is here, and and so it lives with respect to this guy. Okay, so this is the Cryer-Spencer construction. So I guess we could call this the Cryer-Spencer map, right? And what you do is to get the infinitesimal version. So the infinitesimal version is obtained by base changing this. Okay, so in particular, if we take this tangent vector here, so this is S, so the tangent vector, right, this is really the same thing as a map here to S, right, and X sits over here, okay? And so to get your infinitesimal thickening, so the infinitesimal thickening is the thing that you get by taking the fiber product across S over this spec. Okay? And so then, when you have one of these things, the Cryer-Spencer class that I just constructed, or the thing that I talked about in this example up there, is just this construction here. All right. So the KS construction in the example so this is the infinitesimal one. If the infinitesimal deformation comes from base change. Okay.
So it's like there's some fixed vector.
Yeah, exactly. So this is like, so the way you think about this spec, so some people call this, so Momberg calls this a decapitated tangent vector, right? Yeah. And so, yeah, it's like some fixed vector, this is the vector, right? Morphisms from these guys are really vectors, right? And then, because of scheme theory, you can base change by that to get something defined over that guy, right? Okay. So, so that we talked about that, and now I'm going to kind of change gears a little bit. Oh crap. So I'm here, right? Okay. So now I'm going to change gears. How am I doing on time? No. Let's see. I've got to start it.
25.
Okay, 25. Okay. I think we can do this really quick. So I need to tell you about p derivations. Okay? I'm just going to do, so most of you know that p derivations are these operators that Alex Buium works with all the time. And a lot of you guys haven't worked with them a lot, so you forget the definitions. So let me just give you some basic examples and tell you the basic facts that we need. So the basic example to keep in mind is this guy from Z to Z, right? And it's this. This is the guy that we're talking about. Okay, and So let me just say a fundamental fact about these so that we can kind of skirt p-derivations a little bit, is that p-derivations for p-torsion-free rings. Okay, so I guess I should also mention that an operation like that, it satisfies a sum rule and a product rule, which is algebraic, right? It's a nonlinear operation. Yeah, and it exists from something that's, you know, in characteristic 0, or not quite characteristic 0. It goes something from mod p to the n to mod p to the n minus 1. Okay? So, because there's this division by p there. But let me say this is that, so let me say a fact. Okay, so if A is p-torsion free, is a p-torsion free ring, then p-derivations over here are in bijection with lifts of the Frobenius. Okay, so what's a lift of the Frobenius? A lift of the Frobenius is a map, is a ring endomorphism, A to A, right? Such that, so this is for p-derivations on A, okay, so they're endomorphisms. You can have them going from one ring to another ring, but I just want to give you the crash course here. So this guy here looks like A to the P mod P. Okay, so that's mod P times A, so this is A to the P. That's what a lift of the Frobenius is. And to get a P derivation, right, when you have a lift of the Frobenius, you get delta of A, which is this P derivation minus A to the P divided by P. Okay? And these two operations are in bijection with each other. The upshot of working with the P derivations is that they have these sum and product rules, and over here, reduction mod P, so just working with this delta in our signature allows us to reduce mod P. We don't have to keep track about division by P at all. Okay? Okay, and so the last example that I want to give, which illustrates this thing that I told you about going from mod P to the n to mod P to the, or mod P to the n minus 1, is the following. Of a P derivation, and this goes from one ring to a different ring. And here, so we can define delta from z mod p squared to z mod p. And here, you should recall that if you have something divisible by p in this ring, then division by p makes sense, right? But the thing that's multiplied by p is only well-defined mod p, since we're modding out by p squared. Okay, so let me just say that again, is that here, we can define delta of a for a in z mod p squared by, well, we can take a, and we can subtract off a to the p, right? Okay, but now this lives in p times this ring here. And p times this ring is isomorphic to this as a zp module, right? Or z mod p module. Or as a z module even, right? So we can take division here, and we still get a p derivation. So this is still a p derivation. Okay, but it has, it goes from one ring to another. So it goes from, these are two distinct rings, right? And this one's mod p squared and this one's mod p. Okay. Okay, so now we've talked about p derivations. Was there a question? I thought or no? Okay. All right. So, we did p derivations. Okay, now I get to talk about delineal Z classes, and this is the abstract arithmetic Spencer classes that I was intending to construct. So, delineal Z classes. And these are the Kodaira-Spencer classes in the sense of Buium. Okay, so they're going to be our arithmetic analog of the Kodaira-Spencer class. Okay, and so first I need to give you some notation. So notation. So we're going to be working with this ring R, which is ZP unramified completed. Okay, and so what does this mean? So this is ZP, or the inverse limit of ZP unramified mod P to the n. Where we take that limit. I just want to remind you what ZP unramified is. ZP unramified is ZP, right? It's the maximal unramified extension of ZP, right? And what we do is we just adjoin all the roots of unity which are co-prime to P. Okay? Also, I'm going to introduce some other notation. Rn is going to be defined to be R mod P to the n plus 1. Okay? And if X is a scheme, for X a scheme over R, okay? Then Xn is going to be defined to be equal to X tensor over R with Rn. So we're just taking our equations and we're reducing them modulo P to the n plus 1. Okay, so now I come to the definition of the delineal Z class. So, definition. So let X over R be a smooth scheme. Okay, and we're going to let UI cover X. This be a Zariski cover with lifts of the Frobenius, or with P derivations, or lifts of the Frobenius equivalently, with let's say UI from, maybe that is a bad one. Okay, I'm switching notation for my notes, so this could get ugly. Okay, so with delta I from O of UI to O of UI, so these are just the functions. So this is, so let's say Zariski cover of affine opens, let's say. With these guys, lift of, okay, and so here, this is, okay, so I should have done this. So here, let's do this, A, and this is for A, the commutative root. Sorry. Okay? So here, this is the reduction mod P squared, and this is the reduction mod P. Okay? And we'll take these guys with lifts of the P derivation from, so delta from R1 to R0. Okay? So I didn't really say that, but R1 to R0, similarly to this one, also has a P derivation. Okay? But it's given by, instead of doing A there, you have a lifted Frobenius there instead. Okay, so this is the setup. We have a bunch of lifts of the Frobenius, or a bunch of P derivations equivalently lifts of the Frobenius, so I think of them as interchangeably, right? And then we define the delineal Z class of UI and delta I. So we have this cover here. Is going to be defined to be equal to the difference delta J here. And this actually lives in H1 of X0. So this is where the bar came in, right, why we were reducing mod P. Okay, on the Frobenius tangent sheaf of X0. Okay, so this is the delineal Z class. So this is here. Okay, notice that I wrote X here. It actually doesn't depend on the cover and the choice of lifts. Okay, so this is a Czech cohomology class. Okay, and yeah, so one of the things that you can check is that the difference of two p derivations, if you reduce them on p, it's a lift of the Frobenius, yes?
Now the FTX naught is.
Yeah, great. So, excuse me. So an FTX naught is the Frobenius tangent sheaf. So this is just a sheaf of semi-linear derivations where the semi-linearity comes from the Frobenius. Right? With Frobenius. I should maybe call them Frobenius semi-linear derivations. Okay? So this is the sheaf of Frobenius semi-linear derivations. This is just on x0. Okay? So the subscript there denotes where it came from. Okay, so this is our dude. Okay, and now I believe I can state the theorem. So the theorem is the following. Okay, so we're going to have a sort of abstract Kudaira-Spencer map. So if f from x to y is a smooth morphism of smooth R schemes. So I need to use smooth twice. Smooth for this map and smooth for the structure map. Okay? It makes me sad, but okay? But that's what I need to do. Then, maybe someone knows how to fix this. Then, so we have the appropriate compatibility. So we have the delineal Z class of x1. Okay, so I should say that this thing here, this thing only depends on the reduction mod p squared of our original variety, right? Is equal to f star of di y1 here, where let's say as elements of h1 x0, and then we pull back the Frobenius tangent sheaf on y0. Okay? So there's a common recipient space for both of these classes. Okay? And so this is what we want to show. Or that's what we prove. Okay? And so this condition here, we're going to call this condition delineal Z compatible. Okay. Okay. All right, great. All right. So now I am going to talk about the proofs, I guess. So, proof strategy. And how much time do we have now?
10 minutes including questions.
Okay, 10 minutes including questions. Okay, so let's talk about where the hypotheses are used. Okay? So I have two versions of smooth, right? I've got smooth in the map, and I've got smooth in the cover, right? So like these guys are smooth over R, and this is smooth. Okay? So the smoothness for the cover, okay? So X and Y, so about the hypotheses.
Taylor, could I just ask?
Yeah.
So is the statement saying that something is an abstract Kudaira-Spencer?
Yeah, so well, okay, so there's, yeah. So it's saying that the delineal Z class is an abstract Kudaira-Spencer class if I could get rid of the, well, Okay, I could redefine, I could bake it to make it that way if I changed. So the original definition, as I said, that was from the category of schemes, two schemes over things. But here we only have smooth maps, right? So if I could do it for all things, then I would think it would be good, right? But yeah. But that's just the way I define it. I guess yeah. So morally, this is if I redefined that what an abstract Canara-Spencer class was to change the recipient category. If I bake that in there, then yeah. It would say that this is an abstract Canara-Spencer class. Okay? All right. So, so the hypothesis, okay, so about the hypotheses. Okay? So we need x and y over R to be smooth. For the infinitesimal lefting property. Which gives us local lifts of the Frobenius. The Frobenius. Okay, and for the uninitiated, let me tell you what the infinitesimal lifting property is on the level of rings. Or, okay, well actually, let me do the other thing. This smooth map is that we're, okay. So it's kind of just it's kind of a silly thing, right? It's, so the other thing that we use is that, so let me just, so the infinitesimal lifting property. Infinitesimal lifting property. Okay, for rings, A to B is, let's say, formally smooth, has the lifting property. So this is a morphism of rings, commutative rings. Okay, every time you have one of these, where I squared is equal to 0 in here, right, you get one of these. Okay, so there's a diagram that makes this commute. And when you do this for, so what will happen is that you do this for the width vectors, and this is what lets you lift derivations. Okay? All right, so the other thing is, the other smoothness, so if, so the other thing that I want to say is, for f to y, f from x to y smooth, locally, we have this factorization. So this is a projection, right? This is an Étale map, and this map here is our original map F. Okay? So we get this factorization. So I'm writing it like X, but really this is over open subsets. Okay? And so one of the idea is that you know, you prove it for this, and then you prove it for this, right? And then you get the whole thing. So it's kind of, yeah, not really magical. Okay? So, yeah. So again, that's the idea. So, so if we have two morphisms, so we have x to z to y, and we have h and g, where both h and g, satisfy the infinitesimal lifting property, or sorry, satisfy delimital z compatibility, then H composed with, or G composed with H does too. All right, and this is it's kind of fun to check. Okay, so maybe I can do that part, and then if there's more questions, I can say, or maybe not. How am I doing right now?
Alexei said it's non-trivial to have lunch in the 1.5 hour break.
Okay.
We should finish.
So I guess I can leave it here. I guess you can see what the idea is. But the idea is that you locally lift the Frobenius compatibly on open sets, right? And then this condition implies the linear Z compatibility, right? And yeah, and so that's basically the idea. So if you have any more questions, you can ask me afterwards.
Yeah, we still have 3 minutes.
Oh, okay. I've got 3 minutes. Okay.
That's 3 minutes for questions.
I was like, okay, let's do it. Yeah.
So, embedded in this, that you didn't say, of course, is you need to show the linear Z compatibility for restrictions to opens.
Yeah. Exactly. But that's what you're doing, is that you essentially, on open sets, yeah, exactly. You're doing this all locally. It doesn't look like this, but yeah, you do it all locally, and then you do it. Yeah. Exactly. Yeah. But you use jet spaces for that, so that's where you kind of use some technical things about the arithmetic jet spaces. At least that's how I did it. There might be an easier way to do it. Yeah.
You said you tweaked some definition to make, so this would,
Yeah.
this
So.
compatibility is not really some more classical.
Yeah, so let me give you his definition. So his definition, I have it here. So where is it? Okay, so he phrases his, okay, so like I said, there's like the generic version, and then there's the infinitesimal version. There's also the dual that you need to worry about. And so what his original condition was the following, and then you have to disentangle that to see how it's kind of related to this one, is, so if you have x over s, and this is all over a base b, okay? Then, like the diagram that we had, this diagram here of the tangent spaces, you get, so you get, well, I'm going to do it in the cotangent bundle, omega s over b, omega x over b, and then you have omega x over s goes to 0. So you have this exact sequence like this. And so this exact sequence has an x class. The x class is an incarnation of the Spencer class. So this x class is an incarnation, let me write that.
Now that's under the smoothness assumption.
Yeah. So I guess you only get one side, right?
Because you don't get injectivity otherwise.
Yeah, so let's say it's smooth. Yeah. Right? Okay, so and then you get this associated x class. So he calls this kappa of x over s. So this is an h1 x, and then you pull back. Okay, so okay, so sorry. This is x1. Sorry, I have to do this again. So it's an extension of omega x over s by f star omega s over b. And then he views this as h1 x f star omega s over b tensor t x over s. Okay, so you have this class here. And then his condition is that, his condition says that for, if you have f from x to y, then again you have f star kappa of x over s, let's see, y over s is equal to df kappa x over s. Okay, so his is like this, and then so his idea was to try and replace this exact sequence with something else for curves. And if you do it over curves over a number field, you can't have a deeper base, is the idea. So there's no, so in the formulation where you have x over a curve, like over a number field, or like a ring of integers, you can't have a lower b. And so that's supposed to be like the, field with one element, right? So that was his initial condition, but if you impose this condition and you ask if there's like some sort of extension like this, then you show that it doesn't exist. And I guess he does it for like P1 minus some points. So, yeah.
Okay. Let's thank the speaker again. We resume at 1:40.